was late getting started. Of course, I didn't make it down to my office until well after. All right. Go from current slide, but before we start there, let me make these couple of announcements. I made this one before. Have you done your Cedar course evaluations? Not yet? Huh? Not yet. You don't have to do them, but just don't forget about them. Okay? You know how to access them, right? Good deal. All right. The second is this has been going on for a few weeks now, and I've forgotten to mention it specifically because I never knew exactly until the day of it. But I know more precisely now. You know, if you go back and check on my office hours, I stated that they were from on Tuesday and Thursday. Monday, Wednesday, I have almost no office hours. I have half hour in the morning, half hour in the evening, and that's about it. Okay. But on Tuesday, Thursday, I had a block from 10:45 until about 4:30 when I had office hours. Except that the last several Tuesdays and Thursdays, I've had to go over to the Birmingham campus either to get people to sign their evaluations or one thing or another, and that's still continuing. I have one that's supposed to sign tomorrow, so I'll be leaving, I don't know what time yet because I haven't heard from him when he'll be available, but hopefully it could be as early as 2 o'clock to leave this campus, or it could be as late as 4 o'clock. So sometime between there, I'll be going to the Birmingham campus to get an evaluation signed, and hopefully maybe even turn in the evaluations. All right. Then on Thursday, we have a meeting. I believe it's going to be starting around 2:30, so I'll be leaving here by 2 o'clock to get over there by 2:30. The next Tuesday, we have a hearing. I don't remember what time it starts, but it's sometime in the afternoon. I think it's a little bit later, so I may not leave quite as early as I do, as 2, but it'll be between 2 and 4. And then finally, I think by next Thursday, I'll be back to my old schedule. So I'll probably be here until closer to 4:30. I may not wait as late as 4:30 because sometimes I have traffic problems getting over there. So I may leave a little earlier than 4:30, but I won't be leaving as early as I do these last few days. So anyway, my office hours are kind of in shambles until next Thursday. Not this coming Thursday, next Thursday. All right, I can't think of any others that are absolutely necessary, but you said you had a question. Did you want to ask it now or after class?
I can ask it after class. It's mainly about the partial derivatives that I keep getting confused on.
That what?
The partial derivatives that I keep getting confused on. That's what it's about.
Okay.
I can just put after class.
Okay. Well, if you find something in the book about it, I'll be glad to do it, like one of the homework exercises or something.
I just kind of made one up. Really?
Well,
It's we have like sign that in parentheses and how to take a partial derivative in respect to x and then partial derivative in respect to y.
okay. That's the total derivative, though, right?
I thought it was just x and y.
Okay. Well, okay. Is that based on a test question?
Yeah, and I kind of just.
Okay, well then let me find one. Okay, this is test. Not deep enough. Okay, is that it?
No, sir.
No, oh, that's another.
Question here. It was this one.
Okay.
Like I know how to do that part, but I'm getting
Okay, so this is total derivative.
Yes.
Yeah, that's it's not partial, but it involves partials.
Right.
That's for sure.
Okay.
And that was what 13.5. Okay, let's do one from the text in 13.5. Okay. This looks like one fairly similar to what you're talking about on page, oh, you don't have a book, do you? Okay. All right. I'm going to do it on this slide. Let me make sure I've got my pen. No, I don't. There we go. Okay. This is on page 917. This is a 13.5 exercise. And this is problem number 8. And if this isn't close enough, let me know. W is equal to cosine of x minus y Now, can I see that problem one more time? Yeah. And x is equal to t squared, and y is equal to 1. All right. Is that close enough? Okay. And we're looking for dw dt. In these exercises, find dw dt. And that's a total derivative. Okay? Now, by definition, this is the, can you tell me, partial of with respect to x times dx, right?
Yes.
Next.
Plus partial of dw over dy.
Partial with respect to y dy. Perfect. Okay? So that means we first have to do the partial of, well, partial of cosine, I can't write, of x minus y with respect to x. What would that be? It's ugly writing is what it is.
That's why I'm confused. You use the chain rule?
Yes, absolutely. Wait, my pen hit the wrong, there we go. So what's the partial with respect to x of cosine? Yeah, negative sine of x minus y. Then the partial derivative of x with respect to x is 1. Derivative of x with respect to x is 1. So it doesn't have a second part. Okay? So dw dt is equal to, this is the partial with respect to x, so it would be a minus sine of x minus y dx. Now let's do the partial of w, which is this, cosine of x minus y with respect to y. Okay, again, it would be a negative sine of x minus y times, second, partial of y, 1, minus 1, because you see, yeah, so that makes a plus there. So that would then be plus sine of x minus y dy. Okay, does that answer it?
Yes.
Okay. Yeah. Okay. But yeah, the chain rule is involved. It's just the first one, the chain rule derivative of the inside with respect to x is just 1. Well, the second one, the derivative with the inside with respect to y is a minus 1. Now, if that had been a x minus y squared or x squared minus log y or something, yeah, you keep chain ruling and chain ruling and chain ruling. Right?
And then our just take the derivative of x and y and multiply and put them in.
Second.
I said we're gonna plug in the t squared, take the derivative of that and multiply it times the first one and plug in.
I couldn't hear the first one.
I was saying, the t squared here, you just take the derivative.
Oh.
And
Wait.
plug it in.
Yeah. I'm sorry. I forgot to do that part. Okay. It's not just dx. It's, dx dt and dy dt. I'm sorry. I left that part out. Okay. So this will be derivative of w with respect to t, total derivative, is equal to minus sine of x minus y. All right. Here's our first Y chromosome. Davis. Okay. We're doing an example from a previous section, page 917, section 13.5, exercise number 8. Okay. Now dx dt is what? 2t. Okay. Yuck. Here comes 7. We're doing an example from exercise, or we're doing one of the exercise problems from exercise set 13.5 on page 917. We're doing number 8. Okay. Plus sine of x minus y, and what's dy dt? 0. So this whole term disappears. Okay. Now, here's the one other thing. Since you're asking for dw dt, it's better to have your answer in terms of t alone, not your x's and y's. So instead of this, let's plug in what x is and what y is. Okay? So this will be minus the sine of x is t squared, y is minus 1, so it's a minus 1 times 2t. So I'm going to put the 2t out in front because it gets really confusing having them hanging around behind. So I'm going to put minus 2t sine t squared minus 1. So now it's a derivative of w with respect to t. No x's, no y's involved. Now let me make sure that's what they were intending. If I look in the back of the book, 13.5, one of those examples. Example 8's not back there, but let's find one close to it and make sure. (13.5), number 7. Yeah, they put it all in terms of the variable t. Yeah. I thought they would, but I just wanted to make sure that I wasn't telling you something wrong. All right, good deal. Does that answer your question then? Yeah. Any others? All right. All right, then let's go back to, all right, for me to erase that slide. Okay. Area of a plane region. All right. What we're going to do here, consider the plane region R. This is your plane region, the sort of pinkish region here, R, bounded by x equal A on the left-hand side, x equal B on the right-hand side. So all x's between A and B, and between G sub 1 of x on the lower side and G sub 2 of x on the upper side, and those are the boundaries for your sort of your y values, okay, your upper and lower. So what is the area of that? Well, dead giveaway here is that the fixed numerical boundaries, A and B, are along X, so therefore you need to do a dx. That's the giveaway, okay? And the area would be the area from A to B of G2, the upper of X, minus G1, the lower of X, dx. That's it. And that is the area. Now that was what we did back in Cal 2, right? We found the area between two curves that way. Exactly that way, okay? But what you could do is write this as a definite integral itself. That would be the integral of y from dy between g1 of x to g2 of x. So instead of that, write this as a dy here, going from g1 of x to g2 of x. That would be your inner integral, and then this would be the outer integral. The outer integral always has to be the one that you know the definite numerical values for. And that's what makes it a vertically simple region. Okay? You're going from function to function, and that's pretty simple. And you're going from fixed values, x equal A to x equal B. Okay? So this is how we did it back in Cal 2. That's still a perfectly good way to do it. But now that we're doing multiple integrals, you could express it this way. There's no advantage to it that I can see, but there will be problems you can't do this way that you can do that way. Okay? I think we'll run into those. Okay? Okay, specifically, consider x to be fixed, okay? And let y vary from g of x, g1 of x to g2 of x for any given x. And this would be that integral, y evaluated from g2 of x down to g1 of x to g2 of x. And that would be that. And that's exactly what the inner part of that previous integral was. So combining those two integrals, you can write the area of the region this as this. You know, you just evaluate this part in here, g2 of x minus g1 of x here, and that gives you that original area, which is exactly what we did back in Cal 2. I know we weren't all in the same class then, but that's what we did. Now, I think the same thing happened last Monday. I taught all day long with my computer charging, and it kept saying the red light on the battery all day long. I think I told you, or I may not have told you, when I got home, it still was doing that. When we finished this class, I thought my battery must be completely dead. I went home, plugged it in, and started to set up, and in 15 minutes it went out. So I don't know if the plug's not good, I don't know what's going on here, but it's been a red light all day long. And I've been teaching since before 8:30 this morning. Been plugged in and working. Okay, now, placing a representative rectangle in the region R helps determine both the order and the limits of integration. The vertical rectangle implies the order dy first, then dx next. Okay? With the inside limits of integration corresponding to the upper and lower bounds of the rectangle, so your dy's going this way are going from g1 of x to g2 of x, and then your dx's are going from a to b. The fixed boundaries have to be the last boundary, not the variable boundaries. Okay. This type of region is called vertically simple because the outside limits of the integration represent the vertical lines x equal a, x equal b. That's got to be how you do it, and that makes it vertically simple because the vertical lines are the last ones that you do. Vertically simple. Okay? Does that make sense? Just a term there that doesn't really matter that much, but it does. Now this one, similarly a horizontal rectangle implies order dx dy. And why? Because you first do dx's from f1 of, goodness, I can't even read that. That's h1. Okay, no wonder I couldn't read it. It's not L. h1 of y to h2 of y. Okay, and you're doing, h1 of x and h1 of y and h2 of y. You're doing your dx's with respect to that, going from here to here, and then you do your dy from c to d. Again, the fixed numbers have to be the last one. So the x's are going from h1 of y to h2 of y. Okay? So those have to be the inside part and the outside part. That's a horizontally simple because your the y is equal to c, y is equal to d is the last part. Because the outside limits represent the horizontal line, y is equal to c, y is equal to d. Okay. My arm is itching up. Okay, I got eaten up by chiggers weeks ago, and I still have itchy parts of them. Okay. And here's Rachel. Goodness gracious, it's driving me nuts. So here's sort of the summary of what we were just doing. Area of a region in a plane. If R is defined by some A, x going from A to B, those are actual numerical values. As soon as you see this, you know the dx is going to be the outside integral. It's going to be the integral with respect to x, because you have to have those numerical values. And your y is going from g1 of y to g1 of x to g2 of x. Those are your y variants. That's got to be your inside integral, where g1 and g2 are both continuous functions on that whole region A to B, because these are both functions of x, so they must be defined on A to B. Then the area of R is the area from A to B. The outside integral has to be this one with the definite numbers there. A to B, so that puts your dx on the outside, and then the inside of g1 of x and g2 of x, those are your y variables, y limits, so that's going to be the dy on the inside. That's vertically simple. If R is defined by C is less than y is equal to d, you know that's got to be on the outside, right off the top. So that's got to be on the outside. The dy has to be on the outside, and your x's are going from h1 of y to h1 of y to h2 of y, where h1 and h2 are continuous on the interval from C to D. Then the area R of R is the inner first, h1 of y to h2 of y, if you integrate with respect to x, and then the outer integrating with respect to y from C to D. That would then be a horizontal simple, because your y is equal to c, y is equal to d. That's your last outer limits. All right, here's problem 3. Use an iterated integral to represent the area of the rectangle shown in this figure. Hey, this is a piece of cake. It doesn't matter which order you do, and frankly, the answer is almost completely obvious. But you can do it either of two ways. It says use an iterated integral, so let's do it. So what would you integrate? It's going to be a double integral. And what would you integrate? D what? dA, you said? Oh, from B to A. Is that outside or inside? Outside. Okay, so this is from, actually you usually say the lower from first. A to B. C to D. And what order do you put here? C to D refers to dy's, and A to B refers to dx's. That's it. That's all, folks. I wish I could stop itching. Okay, so don't worry about the outer one yet. A to B, we're going to wait on that. Let's do the integral of the big. What is the antiderivative of dy? Antiderivative of dy. Why? Why not? Okay, no, why? Y evaluated from C to D, and then dx. So let's do, not quite ready for this, but A to B. What's the, what would that be? Second? Okay, but we got to do this first. What would that represent?
So you took the integral?
We just did.
Oh, wait. Okay.
But now I'll do the limits. This is y equal d to y equal c. So how would you do that? Okay.
D minus C.
Second?
D minus
D minus c, exactly. Integral of d minus c. I can't write. Let me see if I can clean that up a little bit. Okay. Dx. Okay. Now, d minus c, by the way, is just a number. It's a constant because d and c are both constant. So you can pull that outside the integral and make it d minus c times the integral from a to b of dx. And what's the antiderivative of dx? X. So that would be d minus c times x evaluated from a to b, and that would be what? D minus c times b minus a. Perfect. That is the answer. It's a rectangle whose length is d minus c and its width is b minus a. And it didn't matter what order you did those. You could have done the dx's first, then you would have put the a and b on the inside and the d and c on the outside, and then the dy's last. Yeah, didn't matter. You're going to get the same answer either way. Okay. D minus c times b minus a. So I'm going to erase what I did. Is that okay? Okay. And we'll watch how they did it. The region shown is both vertically simple and horizontally simple because you have fixed values on either. You can use either order of integration. It doesn't really matter. By choosing dy dx, you obtain the following. They just showed dy dx, which you wound up choosing, but you, I think, did it in a different way. You said the b minus a dx out on the outside and the c to d dy on the inside. Did this integral first. That gave you y evaluated from c to d. That's d minus c. Integral of that with respect to x. And that d minus c could have been pulled on the outside or not. Doesn't matter. And your antiderivative of dx is x. And you evaluate that from b to a. So that is d minus c times b minus a. Done. Any questions? Does it make sense? Okay. Notice that the answer is consistent with what you know from geometry. The length of this times the length of that, that's the area of a rectangle. That's the last slide they show. Shame on them. They leave off, goodness gracious, example 4. So let's us do example 4. Use an iterated integral to find the area of the region bounded by the graphs of f of x is equal to sine x, I can't write, and g of x which is equal to cosine x. Okay? Between pi fourths and 5 pi fourths. That's what x is going from. Okay? All right. So let's sort of draw the graphs. I will need to stop messing with it because it makes it itch more, but it's driving me crazy. Okay. Let's draw the graph first. Okay. Now it goes from -1 to 1, both of those. And if this is 0, and let's say is 2 pi, and this is pi, this is pi halves, this is pi fourths. This will be 3 halves pi, and this will be 7/4 pi. Don't need it there. This will be 5/4 pi. I didn't need that 7/4 pi, but I'll put it in anyway. So let's graph those. Sine starts at 0, goes up to +1 at pi halves, down to 0 at pi, down to -1 at pi halves, at 3 halves pi, and back up to 0 here to start over again. So there is approximately your sine curve. I don't draw curves very well. Okay? What color you want to do cosine? I don't want to do the same color. What color you want cosine? Green? The dark green? Okay, cosine starts at 1, goes down to 0 here, down to -1 at pi, up to 0 at 3 halves pi, and back up to 1 at 2 pi. We don't need it that far, but we're going to do it. So it goes down here, and like this, and up to there. Okay? You can go on up to here if you want to, but we're not going to use it. So it's asking for, and by the way, sine and cosine are the same at pi fourths, so that's why we start there, and they're the same but negative at 5/4 pi. So that's why those 2 points were chosen. So we're doing that. Now, do you consider this horizontally simple or vertically simple? Wait, that wasn't what I meant. Man, this happened last class as well. Suddenly got the sneezing fits. Okay. Which you say vertically simple? No one said? Or did you say? No? Okay, horizontally simple would be this way. Here it would be going from one hump to another hump, this to the other, and here to there. That wouldn't be very simple. Vertically, though, yeah, it's going from the lower green graph to the higher black graph. Vertically simple all the way, right? And we know exactly where it begins and ends. Now we knew where it began and ended on the y's too, but it wouldn't be simple because it's going from different parts of the same graph, or it's going from one graph to another. This one's always going one graph to another. So since it's vertically simple, we want our last d's to be your dx's. If the last d's are the dx's, then I do it this way. The dy's have to be before that, and your dy's are there, the dx's are here, and that's going from pi fourths to 5/4 pi. Right? See how you let the problem help you set itself up? Okay. Now, what's going on the inside? Okay, you're doing dy's. And you're going from, the lower curve is your cosine curve, because mark this. The green was cosine, the black was sine, and you're always going from cosine to sine, so that means that your lower curve is the this thing gets all screwed up sometimes. Okay, it's going from and we get my color back. Okay, you're going from cosine x to sine x. You're going from the lower curve is the cosine curve to the upper curve is the sine curve. Okay? And you're just evaluating not any special function in there, you're just evaluating that. So how would you solve that then? What's the antiderivative of y? I mean dy. Okay, you answered my question. Okay. So leave the outside alone. Pi fourths to 5/4 pi. And then this would be y evaluated from cosine x to sine x. And then you have your dx here that we'll do later. So what's the inner integral? Integral from pi fourths to 5 pi fourths. How would you evaluate that y? Say again? Don't put those in yet. You're trying to do this evaluation right there. Yeah. It's what? That's it. Sine x minus cosine x. And then you do that with respect to dx. Now you integrate with respect to x. And what would that be? Antiderivative of sine x is negative cosine x. I can't write. Minus sine x. Is that what you said? Okay, evaluated from pi fourths to 5 pi fourths. Okay? Now, here is where it's helpful that we've drawn the graph already. Because you're evaluating first cosine minus cosine x at 5 pi fourths. What is that value? I don't think so. That value is cosine of, it's a negative. That part's right. Yes, negative square root of 2 over 2, but then you got a minus in front of it, so that gives you, I'm going to have to go up here to do it, that'd be root 2 over 2, that's the first part, minus, and what's the sign there at 5/4 pi? Negative root 2 over 2 again, so that would make it a plus, root 2 over 2. Now we do a minus of a minus, which would be a plus. And what's the cosine of 5/4 pi? I mean, 1/4 pi. Okay? That's root 2 over 2. Minus a minus is a plus again. And that is again root 2 over 2. So that's going to be 4 root 2's over 2, right? And these two will go into that, so that gives me 2 root 2. All right. Now, you could plug that in if you wanted to. That's about 2.14. So that's going to be something on the order of 4.28, approximately. See what they got? They just wrote it as 2 root 2. Perfectly fine. Does that make sense? All right. Example 5. Okay, let me erase. All right to erase, or y'all need it a little longer? Okay. Now, example 5. Now, this one, by the way, especially for those who don't have books, or even if you do, you can go to larsoncalculus.com and see an interactive version, participate in an interactive version of that type of an example. So it says, sketch the region whose area is represented. So this is going backwards. Before we had a region and you find the integral. Now they're giving you the integral and you sketch the region. Okay? And here's the integral. Starts with 0 to 2 and then goes to y squared to 4, and it's dx dy. Okay? That makes sense because the inner integral here has a y involved, so that means you can't integrate with respect to y until you clear that, so the y has to be on the outside. So that's making sense. So now with that in mind, let's draw our graph here. I'm just going to mark off a few points. Okay. Now, I think I'll first do, because I know the y's are going from 0 to 2. So we know we're only dealing from here to there. Okay? Now, we're doing the dx's first, and the x is going from y squared. Okay, x equal y squared. And you can actually write this in if you need to. Whatever this variable is here, that's x equal y squared. That's a graph that looks like this. 0, 0, 1, 1, 2, wait. Those two are right. But then it would be 2 for the y and 4 for the x. So that would be to here. Okay? So it's going to look something like that. Okay? And then your x, the upper region of x is going to be 4. So x equal 4, because this is x equal this is x equal 4. The other y is equal 0 and y is equal to 2 we drew before. So it's going to be between these two and between those two. So that means it's this region right here. That's the area that you're trying to find. So sketch the graph of the region whose area is represented by that integral. Okay? Now, what's going to be your last part of the integral? The dy's. So do your dy's as if they're going this way. And sure enough, they're going from 0 to 2. 0 down here to 2 up here. That's going to cover everything there. And it's going from y squared here to x equal 4 there. X equal y squared here, x equal 4 there. So initially your dx's are going along like that, from y squared to 4. Okay. Now, are we supposed to evaluate it? I guess so. So which do we do first? Which do you do first? I'm sorry? Huh? What'd you say? It may have been right. Always do the inner first. Okay, and what does that give you? Okay? So leave this to later. 0 to 2, that's going to be the last thing you do, the dy. That's going to be last. So just write that down outside. What is this going to be? X evaluated from x equal y squared to 4. Okay? So let's plug in. Leave these alone for now, 0 to 2, dy. I don't need them that far apart, but that's okay. What does the top one give you? 4 minus y squared. Perfect. Now you integrate that with respect to y, and what does that give you? Antiderivative of 4 is, or 4 dy is, 4y minus y cubed over 3, evaluated from 0 to 4, or 2, I'm sorry, I can't read my own writing. 0 to 2, okay. I don't know why I've just suddenly got itching all over. These triggers just drive me nuts. Okay? And what would that be? Okay. Let's 4 times 2. No. Do the upper one first. 4 times 2 is 8 minus 8 over 3. Now, minus 0, because both of those are going to be 0. So don't even mess with that. So this will be 8 is a total of 24 thirds, right? Minus 8 thirds is 16 thirds. Hopefully that's your answer. Let's see what they got. 16 thirds, good for them. Okay? Now, if you were trying to, okay, it says then find another iterated integral using the order dy dx to represent the same area and show that both integrals yield the same value. Okay, well, if you're doing the other one, I'm going to use green again, then your dx's are got to be the last thing that you do. So there you're going dx going from 0 to 4. So that's going to have to be the last integral, 0 to 4, and dx is going to be the last. Okay? And the inner one has got to be going from down here to up there. But you need this to be some function of y. Okay, I'm sorry, some function of x, because you're going to be integrating with respect to x. Well, what is this function here? If x is equal to y squared, how can you write that as y as some function of x? Solve for y. How do you do that? Square root. Take the square root of both sides, and that gives you y is equal to the square root of x. Okay? So your x, the dy's you do first would then be going from 0 to square root of x. So your integral here would be 0 to square root of x, and that would be your dy. Okay? Now, that's the new integral that supposedly just like this one should give you the same value. They don't look the same. Well, they're not supposed to look the same. But let's see if that would give you the same. What is the inner integral?
What is your formula?
What's that? 4. Okay, your last, see, if you're doing your dx's here, that's the last. X is going from 0 to 4. You see? Here's 1, 2, 3, 4. Okay, that's your last integral. Okay. So let's do that one. Do the inner one first. And what does that give you? Integral from 0 to 4 dx. What's the antiderivative of dy? Y, evaluated from 0 to the square root of x. Okay. And this will then be integral from 0 to 4 of, okay, I don't like to integrate square root of x, so I'm going to call it x to the 1/2 power minus 0, right? So it's just x to the minus half dx. And I think I can maybe do that one. What would that be? X to the 3 over 2. Second? Times 2/3. Perfect. Evaluate it from 0 to 4. Right? So when you plug in a 4, I would say take the square root first. Square root of 4 is 2. 2 cubed is 8 times 2 is 16 thirds minus 0. It's going to be 0. 16 thirds. What did we get before? 16 thirds. Look at that. Same answer. Better be. But that's what we got. Does that make sense? All right. Good deal. So that was example 5. All right. There are times when it's not possible to calculate the area of a region with a single iterated integral. In those cases, you can divide the region into subregions so that the area of each subregion can be calculated by an iterated integral, and that the total area is the sum of the two integrated integrals. Iterated integrals. Okay. All right, to erase? All right. Let me go back to black. Okay. Oh, man. All right. Find the area of the region R that lies below the parabola. Y is equal to 4x minus x squared. Okay, and above the x-axis and above the line, y is equal to minus 3x plus 6. Okay, having trouble getting my pen to mark properly. Okay, so I think we need to draw the graph. Boo hiss, but let's do it. Well, I know we're above red x-axis and wrote y-axis. I don't know. Something's wrong with my brain. Okay, above the x-axis and above y is equal to, I think I was looking ahead to that, y is equal to minus 3x plus 6. Okay, now, if it's above the x-axis, I can put the x-axis way down there. All right? Okay, it's not very evenly spaced. That word. I worked a lot outside this past weekend. I was in the bright sun a lot, and also it was very, very hot. And I sweated so much, I got sweat all over my eyes, and they have been stinging ever since then. So it just aches. Okay, so give me an x. Easy x to plug in. Okay, 0 is even easier. When x equals 0, y is 0. Okay, then I heard 1. When x equals 1, that would be 4 minus 1. That would be 3, right? When x equals 2, what would you have? 8 minus 4 is 4. Okay? When x equals 3, that would be 12. Say again? 12 minus 9 is 3 again, right? And when x equals 4, okay, that's down to 0 again. So there's your parabola, approximately. I don't draw parabola very well, but there's your parabola. The x-axis, we got that. And the line y is equal to minus 3x plus 6. Okay, I'm going to have to extend my y-axis up here. I wish I could draw it straight. That would be 5 and 6. Somewhere there is 6. So the y-intercept is 6. The slope is 1, 2, 3, and 1. 1, 2, 3, and 1. Okay, so here, something like that is that. So we're below this, above the x-axis, and above this line. So here's what we're talking about. All right. Now, we've got two choices. Okay? Now, if we do the dx's, then the last integral will be going from 1 to 4. Do you see that? 1 to 4. If you were doing dy's, ooh, yuck. Okay? Because then, here you would be doing from here, so you'd be going from 0 to 3, going from this line to that line, but then up here you're going from this one to the same curve. That's a lot harder to do. Okay? So I think our best bet is to do dx's. Now the problem with the dx's, here you're going from the curve on top to the line on the bottom, and here you're going from the curve on top to the x-axis on the bottom. So either way, you've got two different integrals to do. These two are the easier two. Okay? So we'll do first like this, and then later we'll do like this. Okay? Two different integrals. Okay? Now that's going to be, your last is going to be your dx's. So we know that that last dx is going to be going from x equal 4 back to x equal 1. From 1 to 4. Okay? And that's going to be dx's, because these are delta x's here. Now your y's here, at first are going from this line to that curve, but then here it's going from the x-axis to that curve. So we got two different integrals there. Okay? Now I'm debating whether we do two completely different integrals, double integrals. And the first one would be here, and again, your dx would be going from 1 to 2 then, and you integrate that first. I think that's probably going to be the best way. And then your next is going to go from 2 to 4, and you integrate these. So I think that's probably the way we need to go. So let's back off from what we did and do it. Oh, goodness, my eyes are stinging. this first one is just going to go from 1 to 2. And that will be that's the dx on the outside, and your integral is going from the upper limit is 4x squared minus x squared. It's 4x minus x squared. I can't even read. Okay. That's the upper bound. Goodness, my eyes hurt. And this is going from minus 3x plus 6 to 4x minus x squared. Okay? And then I didn't leave enough room here. Your last one's your dx. So your first one is your dy, and that's where it's going from. Okay. Why do I have... I wrote that twice. Okay. Let me close this up. There's just no reason to take up that much room. Okay. You're doing a dy first and a dx last. Okay. Now that's this part, where you're going from the upper limit of your this to the lower limit, which is your line here, and then you're going from 1 to 2 here, the dx. The second part, so this is plus another double integral, and you're doing the dx is last. I can't get my pen to do right. So that means you're doing your dy first. Now, again, I've left too much room. Okay. This one, your dy's are going from y equals 0 down here, right, up to your curve up here, which is your 4x minus x squared. So your first is going to be 4x minus x squared, just like it was there, but this time it's going from 0 down here. It's not that line, it's from 0. Y is equal to 0. And then finally your x is going from 2 to 4. That is a 4. It's an ugly 4, but it's a 4. Okay? Now, your integrand's the same, just 1. Okay? So we just have to do where you go from there changes that. So this first will be from 1 to 2. What's this integral? Okay, it'll be y evaluated, the upper limit, 4x minus x squared, and the lower limit, minus 3x plus 6. I'm sorry? Yeah, and then you do your dx's out there. Okay, and what were you saying? Then we'll do the second integral there. Is that what you meant? Yeah. Okay. I'm sort of running out of room, but let me see if I can get it. Oh, wait. Yeah, that's right. The second integral, and the 2 to 4 we don't mess with yet. And this again will be a y, because the integral of that y, dy is just y. But that's evaluated from 0 to 4x minus x squared. Okay, and then you have your dx at the end here. Now I know this is getting a little messy, maybe a lot messy. But do the evaluation. I don't know where to go. What I think I'll do is erase a little bit up here. I don't need that part. And maybe that'll give me enough room to work. Alright. You have the integral from 1 to 2. Alright. How does that evaluate? Right, for the upper one, instead of y, we put that in. So that would be 4x minus x squared minus, let me get my pen straightened out. Okay, now minus a minus is going to be plus 3x, but then a minus 6, right? All right, now we can simplify that a little bit. 4x and 3x is 7x minus x squared minus 6. You okay with doing that? Okay. We'll come back and put that in a minute. Okay? And our last integral is going to be dx, and we'll come back and put that in there instead of stringing it out like this. Okay. Alright. Plus the integral from 2 to 4. Now what will this one look like? That's just going to be the 4x minus x squared, a value, well, dx, sorry. Okay. Now, the reason is it's minus 0, okay? And that's easy. Don't put anything there. This one, the lower limit was that, so we had to put it in the bottom, but subtract it as well, okay? So, that's that. Now, I think I need to erase some more. Well, no, maybe I can get them over here. This will be the, here's the integrand now. So, I'll probably have to write it again. Integral from 1 to 2 of 7x minus x squared minus 6 dx. Okay, I'll come back to that if you want to. Plus the integral from 2 to 4 of 4x squared minus 4x minus x squared. I was getting my things crossed up. Goodness, my eyes hurt. I can hardly see. Okay, dx. Okay, now at some point here, I may have to go rest my eyes out because they are just stinging like crazy. I do not know why. Now my wife thinks it may be that I got sunblock in my eyes because I put sunblock on before. Boy, it's driving me nuts. I did put on sunblock this morning, but I've not been sweating any, so I don't know. So if it's okay, I think what I'll do is erase this line right here. Is that going to be all right? Okay. And we'll try to do our evaluation. Go and take that out too. Let's see, I need that to stay in. Yuck, I lost it. Okay. If I can go back and get that point back in, that line back in. Didn't quite hit it well, but close. Okay, doing this integral up here from 1 to 2, what does that give me? This one up here. This integral up here. It's what?
14.
I think it's 7 halves, isn't it? Isn't that right?
We're integrating, I'm sorry.
All right. Okay. Minus x cubed over 3. Is that what I heard? Okay. Minus 6x. And that's evaluated from 1 to 2. Okay, sorry. Extraneous line there. Okay, plus, now let's do this one. Second? Over 2, so that would be 2x squared, right? Minus x cubed over 3, just like we had before, and that's evaluated from 2 to 4. Okay. All right. Let's plug in the 2 first on the first one. I think I want to write underneath it, so I think I'm going to clear me some more space down here. I was going to write over there, but that's sort of a long way away, and it's easy to miss terms. So I hate to erase this much, but I'm going to. Y'all probably all got it written down. Okay. Let's get this one done. I need to take a break because my eyes are just giving me crazy. Okay, let's plug in a 2 here. What do you get? 2, no, it's 2, it's x squared. It's what? 28 over 2, which is 14, right? Minus 8 over 3, minus 12, minus a 7 halves, right? Plus what? 1/3. Minus a minus is a plus again. 6. Okay? We're going to come back and mess with that in a minute. Let's do this one first while we're here. 2 times x squared, well, x is 4. That would be 32 minus, anyone remember what 4 cubed is? 64 over 3. Okay. I had the minus and I changed it to a plus, changed it back to a minus. This is driving me nuts. Okay, when you plug a 2 in there, you get what? 8. It'll be a minus 8, but then it's going to be a plus when you put 8/3. All right, now let's see if we can combine anything. Okay, this is going to be a plus from here. Well, right off the top, you see a minus 8/3 and a plus 8/3, so it's good to get rid of those. Okay. Now 14 minus 12 is 2, minus 7 halves, and plus, say again? All right, just a minute. oh, there's some, there's a plus 1/3 minus 64 thirds is a minus 63 thirds, which is 21, isn't it? That looks like an awfully big number. Okay? Minus 63 thirds, which is 21. Okay? And then we have plus 8 and a minus, plus 6 and a minus 8 be a minus 2. Now, it looks like to me I've gotten some signs wrong. Because this is obviously going to be a positive area, and I have it coming up being a negative area. I know that can't be right. What's that again? 15 halves. That's it, exactly. But I don't get it out of my calculations here because I've got something that I'm missing. I've missed a term somewhere here, and by goodness gracious, I can't see well enough to. Oh, it's the 32 I'm missing. There it is. I completely lost my 32 there. Okay, let's do a plus 32 here, and that's going to be an 11 here. Okay, I think that's going to work now. 11 minus, nope, that's not enough. Anyway, you're right, it comes up 15 halves. Okay. This sounds like a great time to take a break, doesn't it? All right, that was example 6. But before I do, let me give you the homework exercises in 14.1. Okay, any of the odds 3 through 9, they're all at Calc Chat. 3's at Calc View. Any of the odds 11 through 27, they're all at Calc Chat. 15's at Calc View. Either 29 or 31, they're both at Calc Chat. 33 or 35, they're both at Calc Chat. 33's at Calc View. 37 to 41, they're all at Calc Chat. 37's at Calc View. Any of the odds 43 to 49, they're all at Calc Chat. 51 to 59, they're all at Calc Chat. 53's at Calc View. 61 to 65, they're all at Calc Chat. 67 and or 69 are exploring concepts, so I don't know if you'll have a lot to do on those, but they should be at Calc Chat. Any of the odds 71 to 75, they should all be at Calc Chat. 77 should be at Calc Chat. 79 is a true false, it should be at Calc Chat. Okay, we'll stop there unless then pause. I've got to go rinse my eyes out because they're stinging like crazy. We'll come back and start 14.2. Any questions? Yeah. Okay. Anyone else need a copy of test 2? Okay, I think it says on the top test 3, but it's really test 2. Okay. I taught this class another term that they weren't as far ahead as y'all are, so they had 2 tests before this one. Y'all have 1 before it. Here we go, finally. I may not be deep enough. Let's see. Nope, I'm not. hard for me to see. Does someone have this in front of you? I don't think that's the right test. I have so many different ones. Here we go. Chapter 13 test, right? Yes, that's it. Test. Okay. I did have it right. Okay. Let me back up. Oh, I know what the problem is. They weren't stapled. Okay, here we go. Here we go.
What are the sections for these problems?
What's that?
What are the sections for the problems?
Okay, hold on just a minute. This is chapter 13. Okay, the first two, let me take a look. First, okay. Okay, the first one is 13.1. Second one is 13.2. This one is 13.3. Number 3 is 13.3. And the fourth one is 13.3. Okay, the fifth one is 13.4. Okay, flip the page. And the fifth one's 13.4. Okay, the sixth one I think is 13.5. Yeah.
7.
7, yeah. I think it's 13.5. Eighth one is 13.6. Ninth one is 13.7. And the 10th one is 13.8. Okay. All right, glad to. Okay. Now, what was I going to do? Going to clear the screen. I think. Yeah. Discard that. And clear that. And go to 14.2, and that's where we'll start when we come back. All right, we are now recording again. Let me get my pen set up for black again. All right, we're still in chapter 14, which is multiple integration. And this time we're doing double integrals and volume, okay? Last time we were just doing iterated integrals. Nothing was in there as our integrand, okay? Now we're going to have something in there in our integrand. That's what 14.2. So we'll use a double integral to represent the volume of a solid region and use properties of double integrals. Okay, we'll talk about those. We'll evaluate a double integral as an iterated integral, similar to what we just were doing, and we'll find the average value of a function over a region, which is something very similar to what we did back in Cal 2. Now, I don't think I had any of you for Cal 2, but you should have done it there. Okay? So, double integrals and volumes of a solid region. All right. What I hope you know is that a definite integral over an interval, okay, the words now, integral over an interval, uses a limit process to assign measures to quantities such as areas, volumes, arc length, mass, and so on. In this section, you'll see a similar process to define a double integral of a function. This was a definite integral. That's what we meant by definite integral. Single integral, a double integral of a function over two variables over a region in the plane. Okay? So, here's generally what we've got there. Let's say we have a region in the plane, which would be the floor here. Okay? You have a function that depends on both the x's and the y's, so it could be going up this way or doing whatever it wants to do there. And what you're doing is integrating a element in the plane, but now it's going to be a little square or a rectangle. Okay? And then evaluating here, and then you're going to sum all those up with respect to x and y and get the whole volume that way. Okay? So, consider a continuous function f such that f of xy, now we're going to start with it always greater than or equal to 0 for all the xy's in a region R in the plane. Now your region R is down here in the xy plane, and your function f of xy is something up here. Okay? Z is equal to f of xy. And it's always positive, something above the xy plane there. Okay? The goal is to find the volume of the solid region lying between the surface given by z is equal to f of xy, that's the blue surface here, and the xy plane shown down here, that's that region R in the xy plane. Okay? Now, you can begin by superimposing some type of rectangular grid down here over the region, the xy region. So you're going to split your x's into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares. Do your y's into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares. So a 10 by 10, or whatever you want it to be, a region here, a square region here, a rectangular region, technically, but that could be a square. And the rectangles lying within the R form the inner partition of R. Okay? So anything in here forms that partition. Now some of these rectangles aren't even under the curve. So they're probably not going to contribute anything. The curve doesn't go out that far. Others of them are partially in. The ones that are totally in are going to contribute totally. Those that are partially in are going to contribute a little bit, and those outside are not going to contribute at all. Okay? So the rectangles lying entirely within the R form the inner partition delta. And the norm of that is the maximum partition delta, defined as the length of the longest diagonal of the n rectangles. So if all these little rectangles here do the longest diagonal of any one of those rectangles that are in there, that's going to be your norm. The length of the longest diagonal of the n rectangles that form that grid. And again, we just did this in Cal 2 when we were doing regular integration. Cal 1 this morning, doing regular integration. We're doing the same type of thing, and it really doesn't matter because what we're going to do is let the n go to infinity, so your del, the longest rectangle is going to 0. And longest diagonal of the rectangle is going to 0, so it's going to all take care of it themselves anyway. But anyway, that's how we go. Next, choose a point, x, I, y, I, somewhere here in that rectangle, okay, and go up, and whatever its value is, f of xy, xi, yi, okay, in each rectangle, to form a rectangular prism whose height is that f of x, I, y, I, and whose width is delta x, delta y, dx, dy. Because the area of the ith rectangle is delta I, delta ai, kind of hate they do this because they use this delta back here to be the inner partition delta, and then they're using delta A, meaning a change of A, okay? And that's not the same delta. This is an expression here. Wish they'd have come up with something else. But this is the area of the ith rectangle. The length in x times the width in y, that's the area of that rectangle. We call it delta A sub I. And it follows that the volume of the ith prism, whichever one this is, okay, this is the height times the area. The area is the delta A, and then the height is that. So that's the whole volume of that. Now, get this now. These counters are a little bizarre. This could be the first one here. That could be the second, third, fourth, fifth, sixth. You can count them any way you want to, but it's not x sub I, y sub I. That's what it looks like it is. It's not. This doesn't have to be the same. This is just the ith one out. That could be the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13th one out, or something like that. And the x sub I and y sub I, that just means that's the xy for that one, okay? So it's a little different from how we used to do our subscripts, okay? Now, as you approximate the volume of the solid region by a Riemann sum of the volumes of all n regions, then your summation is I is equal 1 to n of your, and you have a total of n squares, n rectangles in that thing. So that's what your x sub I, y sub I is, okay? And your a sub I. You're doing all n of those shown here, and that gives you an approximate value, okay? Now the red pieces are ones that are sticking up beyond that, and the gaps here are ones that you don't have enough space for, okay? So some are too big and some are not big enough. That's approximately that approximation can be improved by tightening the mesh on the grid. In other words, form smaller and smaller rectangles, and they show it in example 1, and we'll get to that in a minute. So if you had smaller and smaller rectangles, then they fit even closer to what under the grid would be. Your grid will now, let's take half of that space every time. So then you get more rectangles. So you'd have more rectangles covered here, so you fill up more of that space there. Okay? And here's example 1. Okay? Approximate the volume of the solid lying between this paraboloid that's not a paraboloid, okay? No, it is. Z is equal to 1 minus 1 half x squared plus 1 minus 1 half y squared. That is, if you had written this over here and multiplied everything by 2, well, you wouldn't have to do it by 2, but you'd have x squared over 2 plus y squared over 2 is equal to z, plus z is equal to 1. That would be a parabola. That's right, because the z is to the first power. Yeah. Now, this paraboloid is opening downward, okay? And the square region given between, x is between 0 and 1, and y is between 0 and 1, okay? And it says use a partition made up of squares whose sides have a length of 1/4. So you'd have 4 in here, 0 to 0.25, 0.25 to 0.5, 0.5 to 0.75, and 0.75 to 1. Same here, 0 to 0.25, 0.25 to 0.5, 0.5 to 0.75, and 0.75 to 1. So you have a total of 4 by 4, so 16 squares in there. And you're doing the paraboloid over that partition, okay? Now, all those have the same size down here, so your del is just the size of any one of them. Okay, so begin by forming the specified partition in R, And we did that. Okay? Now this is going back to Riemann sums, so they're pretty obnoxious. I'm sorry, did I say that out loud? Okay. And I don't know if I mentioned this to you, but I did, I think, in my last class. Last Monday, for some reason, the entire day, I had the battery plugged in. It seemed like it was charging, but my battery light stayed on red all day long. And I got home and thought, I'm going to have to charge this thing all night. So I plugged it in, did a couple of things, looked back at it, and in 15 minutes it quit charging. It was totally charged. And it's doing the same thing today. This has been red all day long. And I bet you if it stays on all day, I go home, plug it in, and it's going to be totally charged. I don't know what it's doing. It should be charging right now. It should have been charging. I started before 8:30 this morning. It's been plugged in constantly. Still says the battery's red. I don't know. So begin by forming the specified partition. Okay? Now that partition is a quarter by a quarter from 0 to 1. So here it is. For this partition, it's convenient to choose the centers of the subregion. So if you do center to center, okay, the first one is from 0 to 1/4, so it's going to be 1/8. 0 to 1/4, it'll be 1/8. And then 0 to 1/4, 1/8, and on the y, 1/4 to 1/2, that would be 3/8, and then 1/8, 5/8, 1/8, 7/8. 3/8, 1/8, 3/8, 3/8, 3/8, 5/8, 3/8, 7/8. 5/8, 1/8, 5/8, 3/8, 5/8, 5/8, 5/8, 7/8, and 7/8, 1/8, 7/8, 3. So those are your partition. Those are the boundaries of it. Okay? The x given here, the y given there. Okay. So those are your partition. Now let's hope we don't have to do this for a whole lot of them. So what we're going to do is do a sum over all these 4 by 4, that's 16 partitions. Okay? And because the area of each square is 1/16, because it was 1/4 by 1/4, so it's 1/16, you can approximate the volume by the sum, and this will be your f of x1, y1, where it doesn't matter which order you do these, but there, if you do that 1, 2, 3, 4, 5, 6, 7, 8, or whatever, or 1, 2, 3, 4, 5, 6, 7, however you count them off, the area is always 1/16, and the f of that would be, back to your, this, 1 minus 1/2 x squared minus 1/2 y squared. Okay? That's what you're going to plug in for each one of these. Okay? Now, you're taking those midpoints. So that would be the summation from 1 to 16 of 1 minus 1/2 x sub I squared minus 1/2 y sub I squared times the delta A, which is 1/16. You can pull that 1/16 out of the summation if you wanted to. That would be perfectly fine. It would make a lot of sense to do that. And they don't do the work, they just tell you that's the answer. That's not really very fair, okay? Because what you had to do was plug in every one of those xi values with its yi value for all 16 of those and do this. For them to do, that's approximately 0.672. That's not fair at all. I mean, that is ludicrous. I'm not about to go and calculate all those numbers, but for them to just do that and say that's what you got. Okay? Now, later we're going to do the actual calculation and find out its point is 2/3. It says see example 2, so we'll wait and do that. Okay? You can obtain a better approximation by using finer partition. For example, with a partition of squares of size 1/10, the approximation becomes 0.668 rather than 0.672. So it actually gets a little bit closer to 0.667, which is 2/3. That's a very good approximation. Okay? Now, They have a little blurb here on technology on showing these. That's a real pain, though. You can look at that if you'd like. Okay? Now, there is the approximation of the graph. And again, here's the actual curve that's coming down here. So you see this partition overestimates where you see the purple and underestimates where you see the blue. So you can almost take this one and flip it over on most of those and come up fairly close to being not too bad. That's not far from 0.667, so you're not far off. It's overestimated a little bit. And you see a lot of these are pretty big on the edges here, so these are overestimated a little bit. Okay? All right. And they say the exact volume is 2/3. We're going to come back and actually do it. Okay, I think. You can obtain a better solution by using finer partition. For example, okay, and this is what I just read to you before. If you use a partition of 1/10 rather than 1/4, your approximation is 0.668, which is really close to 0.667. Okay. In example 1, note that using finer partitions, you obtain better approximation of volume, just like we did with smaller delta x's or dx's before. This observation suggests that you could obtain the exact solution by taking a limit. And that's exactly what you're doing. Remember, this is the, what did they call that? The norm, which is the maximum diagonal that you have of any of our partitions. We use all the same size, so those are all the same. As that norm approaches 0, the biggest one is going to 0, all of them are going to 0. Then you sum all those up, I is equal 1 to n of all that, and guess what you're going to get? This becomes a double integral now, 1 for x and 1 for y. In fact, your dA is dx dy, right? Change of x by change of y. And your f of x, y in there. That's exactly how we're going to wind up doing it. The precise meaning of that limit is that the limit is equal to L. For every epsilon greater than 0, there exists some delta greater than 0, such that when the difference between L and this thing is less than epsilon, for all the partitions del in a plane region such that the magnitude of again, I'm going blank on the word they use there. The maximum of those is less than epsilon, and for all possible choices, that's why in the ith region. Okay, it's the same as we've used in integration, differentiation, all before the epsilon delta technical definition. Using the limit of Riemann sums to define the volume is a special case of using a limit to define a double integral. The general case, however, does not require that the function be positive or continuous. Later, we're going to come back and say it needs to be continuous, but for it to be positive, that's not going to be required anymore. So here's the definition of double integral. If f is defined over a closed, bounded region R of the xy plane, then the double integral of f over R, so now the only thing different now is we have a function in here. So the double integral over that region R of the function times your dA, which is basically dx dy, that's your dA, norm, that's what you call it. The limit as the norm approaches 0 is the largest diagonal of any of your partitions is approaching 0. And if the largest one's approaching 0, they're all approaching 0. Of the summation, so you see the double integral was a summation. Now, it seems like to me they should do one of these for xi's and one for yi's. Then this looks like it makes perfect sense then. And there's your delta AI. But they just do a single one. Provided that the limit exists, if the limit does exist, then alpha is integrable over R. Having defined the double integral this way, you'll see that a definite integral is occasionally referred to as a single integral. And I don't know a definite integral. I think they'll show an example. That's some Weasley wording here. Sometimes you will see they occasionally referred to, that's a lot of weasel words there. Sufficient conditions for the double integral of f on the region R to exist are that R can be written as a union of finite number of non-overlapping regions, okay, subregions. And here's sort of an example of that, okay? Now these overlapping regions need to be either vertically or horizontally simple, okay? Now, here's your region, and that's a mess because you don't have a definite thing anywhere here. But for this first region here, you can go from the upper to lower and everything, I don't know. If you define the upper curve here to be one function, lower curve another, and then do your dx is this way, then that would be simply vertically simple. This one, same thing, define this upper curve here, the lower curve there. Now what I haven't figured out is that why, oh yeah, I guess let's see. If you chose this as your upper curve here, well, I say going from this, you wouldn't even need two regions. But they say if you can't do it otherwise, split it into two simple regions, non-overlapping subregions. Okay? This means that the intersection of two non-overlapping regions is a set that has an area of 0, meaning the intersection means what do they have in common? Nothing. Okay? In this figure, the area of the line segment is common to R1 and R3. The area of the line segment is 0. So those are non-overlapping. I don't know why they're going into all this, but later they'll make more sense. Okay? A double integral can be used to find the volume of solid of a region that lies between the xy plane and the surface given by z is equal to f of xy. So here's the volume of a solid region. If f is integrable, that's required, over a plane region R, some sort of region down here. It doesn't have to be square or rectangular, but some region R. And that now here we're going to require that f of xy be greater than or equal to 0. Otherwise, volume doesn't make sense. You have to have a positive volume. So the height has to be positive, or at least non-negative. For all the xy's in R, then the volume of the solid region that lies above the R and below the graph is V is equal to the double integral over that region R of f of xy dA. Now, again, what is dA? dx by dy, or at least that's one representation. F of xy, whatever that is, and you integrate. Now, you choose whether you're going to integrate dx's first, or the dx dy, or if you're going to do dy's first and then do y dx. It doesn't really matter, but you'll make that selection, depending on what makes the most sense. Now, I keep thinking, nope, still haven't done a second example yet, so we'll get to it in a bit. Double integrals share many of the properties of single integrals, and here's just a few of them. If f and g are both continuous over a closed bounded plane region R. Now, remember before they said they don't need to be positive and continuous. The last example said they had to make them positive again. Now they're going to make them continuous again over a closed bounded region, plane region R. Doesn't have to be rectangular, just some region R. And C be any constant. Okay? Then the double integral over that region R of C times f of xy, continuous function here. If that's a constant, pull it outside the integral, just like you used to do, and just integrate over the part that's functions of x and y. And then multiply that by the c. Or, the second one, the double integral of the sum of two functions, sum or difference of two functions, over some fixed area, okay? is the sum of the difference of their integrals over that same region. Okay? Sum of the double integral of alpha dA plus or minus the integral of g of x, y, dA. This one, and by the way, these two together are your linear properties. You don't need to know that, but just letting you know. The integral over r of alpha of x, y, dA is always greater than or equal to 0 if f is always greater than or equal to 0. Now, we assumed that earlier that we had volumes, and we're not necessarily talking about volume, but if this is always greater than or equal to 0, this one has to be greater than or equal to 0, because it's over some fixed 0. Okay, the double integral over some region r of alpha of xa, alpha of x, y, dA is greater than or equal to the double integral over g of x, y, dA if f of x, y is always greater than or equal to g of x. So if you're integrating something that's larger than the other, then the integral is going to be larger than the other. Okay? And then this one, the integral over a region R of f of x, y is the double integral over some R1 of f of x, y, dA plus some the region R2 of f of x, y, dA, where R is the union of two non-overlapping subregions, R1 and R2. Okay. Now, my computer is, well, it seems to be okay now. It was fluctuating, but now it seems better. All right, so now we're going to do evaluation of some double integrals. Okay? Okay. Consider a solid region bounded by the plane z is equal to f of xy, which is 2 minus x minus 2y, and 3 coordinate planes shown here. xy plane, xz plane, yz plane. Okay? Now, so it's everything in what you would call the first octet here. Okay. Now here's how I go about identifying these points. Okay? Let's say when x and y are both 0, then z has to be 2, right? Well, when x is 0 and y is 0, you're at the origin, go up here to 2. So you have 0, 0, 2 is that point. So let's now set z equals 0, y is equal to 0. That would give us x equal 2. So 2, 0, 0, 2 for x, 0 for x. Okay? There's another point on corner point, vertex. Then set z equals 0 and x equals 0. And then you have 2 minus 2y is equal to 0, so y must be 1. So 0, 1, 0 is right there. Okay? Now, if 0, 0, 2, 0, 0 is here, and 0, 0, 2 is there, then this line here must be just don't count the y's at all. They're sort of out of the picture, okay? And then you would have a line whose y or z-intercept is 2 and who has a slope of minus 1, because so this would be z is equal to 2 minus x, okay? Because you're going back 2 for every one you go up. Lost another, okay? Okay? To get this one over here, well, actually the easier way to do this is just set y is equal to 0, you have z is equal to 2 minus x, right there. Set x equals 0, and you get z is equal to 2 minus 2y. Okay, where is that? They didn't draw those other ones, but you could have done that, okay? You don't have to do them all, you just need one, okay? So here's what we're going to do, okay? Once you got this line here, what you're going to do is start with dy's, okay? And you're going to go from your base down here, this is where z is equal to 0, and down here, your x is equal, when z is equal to 0, x is equal to 2 minus 2y, okay? Well, they're not doing that, they're doing the other one. Y is equal to 2 minus x divided by 2, and that's what we got here. So there's your base. Y is equal to 2 minus x divided by 2. Okay? So, you're going to go from y is equal to 0 to y is equal to 2 along boy. Okay. What they're doing, the A of x here, is the area of this little triangle here. The base of that triangle is 2 minus x over 2, and the height of it is your z value here, 2 minus x. Okay? So the integral from 0 to 2, you're going to do these little triangles that you have here times your dx. Okay? So the area of those triangles, that's what they're getting at, and the volume is the sum of all those. That's what they meant by getting it down to a single integral. This is not necessarily the easy way to go, okay, but it works, okay? Now each vertical cross-section, taken parallel to the YZ plane, is a triangular region whose base has a length of 2 minus x over 2, that's what we saw there, and the height is 2 minus x. This implies that for a fixed value of x, the area of the triangular cross-section is 1/2 that base times this height. Okay? So 1/2 of that base times this height, and that gives you denominator 4, and 2 minus x times 2 minus x and 2 minus x squared. So there is your area of that little triangle. Okay? All in terms of x, and then you're going to sum that from 0 to the value on A by the formula for the volume of a solid with known cross-section. The volume is A to B of A of x dx. Here was your area, 2 minus x squared over 4 dx. And then they say substitute, and you can certainly do that. 2 minus x being your u, and doing that. So you get minus this thing cubed. The minus comes from the undoing the chain rule here, that's where the minus comes from. And if you make this a cube, then you put that over 3, so 4 times 3 is 12. Evaluate that from 0 to 2, and that's where you get your 2/3. Now, if you remember back, they said the exact value of that was 2/3, and this is how you get it. Now, this is not a particularly clean, or I think neat way of doing this, but here's what they're saying. Your last integral was 0 to, this A here is this base times this height. And you're doing a dy this way. Okay? Now, this picture isn't matching this too well, and here's why. They've got the whole surface here listed there, whereas they had the height listed before, which is 2 minus x for a given y. This procedure works no matter how a sub x is obtained. In particular, you can find a sub x by integration is shown, and that's what this is showing. This is how they got this a sub x here, is by integrating from y is equal to 0 to y is equal to this value, and you're going from z is equal to 0 to z here. So this height here is that. That was the plane they gave you to begin with. So that's what, and you're integrating from that. You're integrating with respect to y, so your x's stay in there, and that's how you got your x's here. So they did it one way, and now I'm showing you that it's the same as another. I find this approach a little confusing. Okay? It's right, but I can see how it can be bothersome. That is, you consider x to be constant and integrate this thing here from 0 to that, okay, which is your y value. And so that's what you integrate first. Your function here, your z, dy, and y is going from 0 to the outer part, which is 2 minus x over 2. And when you integrate that with respect to y, you treat the x as if it's a constant. So 2 minus x is a constant times y minus, and then the antiderivative of 2y is y squared. Integrate that from here. And you only plug in this for the y. So the 2 minus x stays the same. And then this will be times, plug this in, 2 minus x over 2 minus 2 minus x squared over 4. And they skip so many steps here. This is pathetic. Man, let me fill in the gaps here. I really dislike the way they do this. Okay. This will be 2 minus x times 2 minus x over 2 minus 2 minus x over 2 squared. Okay? So this is 2 minus x over 2. 2 minus x times 2 minus x over 2 minus 2 minus x over times 2 minus x over 4. So that would give you 2 of these to make that a 4 down here and subtract them. So yeah, that is correct, but they skipped a lot to get there. Combining those results, then you have the iterated integral. The volume is the f of xy, which is your thing that you had in the middle here, times your dy first. Dy is going from between those two values, 0 to 2 minus x minus 2, and then finally do your dx, 0 to 2. Okay. That's the bottom line. That's how you get there. Now, this middle part is the part I think their description has been a little vague on. So let's see if we can do this. To understand the procedure better helps to imagine integration as two sweeping motions. For the inner integration, the vertical line sweeps the area of a cross-section, and for the outer integration, that triangular cross-section sweeps out a volume. Okay, so they start with a vertical line here coming down this way. Okay, and it's going from the z value here, which is exactly what they gave us, and you're doing dy's here, and you're just sweeping out that portion of it. This function going from 0 to the value out here. Okay? Now, the second part then is taking that and sweeping this way, and now you're going from x equals 0 to x equals 2 or whatever it happens to be here, and you're integrating that portion. Just that triangle, the area of that triangle sweeping this way. That gives you the whole solid. Now what they did I think even this has a poor job of describing, is how they show this on this curve, on this slant line here, and they sort of neglect how you got that weird expression in y, okay? The illustration is great, but they really miss some details. So let's see if we can get something that makes sense, okay? It seems like to me they're going almost in circles here, and there's really no reason for it. But before they do the next example, here is Fubini's theorem. There's another potential paper topic. Who in the world is Fubini? And how did he develop this theorem? That would be another one. What's it used for? Wherever. Okay. Let F be continuous. That's all that's required. Continuous on some plane region R. Plane region R down here, alpha is above it. Alpha is a function of x and y. If R is defined as A to B on x, but G1 to G2 on y, where G1 and G2 are continuous on A to B, okay, that's where x is going from A to B, then the integral over the region R of f of x dA, okay, finally this is back to the point of almost making sense from where we started before. Now we have this function in here. Before we didn't have a function. We just did this iterated integral. Now we have a function in here, and the y's are going from G1 of x to G2 of x, and the x's are going from A to B, and you're integrating this of alpha of xy, whatever that overall function is. Okay? Now, if R is defined rather from y is c to d, but x is going from h1 to h2, then reverse those. Do the dx's first, going from h1 to h2 of your f of xy, and then do your y's going from c to d. So you can do these either way, whichever makes the integration easier. Whichever of these is easier to define. Okay? That's Fubini's theorem. So let's do one. Finally. Okay. Now, this is one over a rectangular region. It doesn't matter what order you do it. Not matter at all, because they're all on the rectangle. So what we'll do here is the integral, and they're both going to be from 0 to 1, 0 to 1, of 1 minus 1/2 x squared minus 1/2 y squared. Now, I was wrong before. The other wasn't the 2/3. This is the one that's going to wind up being 2/3, I think. But let's see. Now, do you have a preference whether you do dx or dy first? It really doesn't matter. Which way you want me to write it? Pick one.
You said starting inside first.
Say again?
DX.
Yeah, let's do dx first and dy. Now, why doesn't it matter here? Because they have the same limits. X and y are both 0 to 1, so it doesn't matter which one you do first. We're going to do that. Since you chose this, though, now that makes your integration different. Okay? Because the first one we're not going to do, 0 to 1, and this is your dy. We're not doing that. We're going to do this one first, right? Because that's the interior one. So now your antiderivative of 1 with respect to x. And what's the antiderivative of 1 with respect to x? X minus antiderivative of minus 1/2 x squared with respect to x. Okay, over 3, but you also had a 1/2, so this makes it over 6, right? Yeah, you can do it in 2 steps if you want to. I'm just saving some steps here. Okay, now the next part is maybe a little trickier. You're integrating this with respect to x. Well, if you're integrating with respect to x, you treat the y as if it's a constant, right? So this will just be minus 1/2 y squared, the constant, times x. Do you see that? Since you're doing this, it's x equals 0 to x equal 1. Sometimes with double integrations, it's better to put those in so you keep in track of what you're doing. So you're evaluating this integral from x equals 0 to x equal 1. Because they have the same limits, it may be good to do that. And these are y is equal to 1 and y is equal to 0, because you're doing that one with respect to y. So this will be the integral from y equals 0 to y equal 1. But let's evaluate this. When x is 1, that would be 1 minus 1/6 minus 1/2 of y squared. Because the y, you don't evaluate. You're going to wait and do that on the last one, right? Okay? So that's the upper one. And guess what? The lower ones are all going to be 0. Because x will be 0 here, 0 there, and 0 there. So those will all go away. And this is what you're evaluating now. I mean, you take that integral dy. Well, 1 minus 1/6 would be 5/6, right? Okay? So we can integrate that now. What is the integral of that? Integral of 5/6 dy would be, that's just a constant. Integral of a constant dy would be, yeah, that would just be y. So that would be 5/6y minus 1. Second? Antiderivative of y squared. Yeah. Y cubed over, and you already had a 2 down there, put a 3 with it, and that gives you another 6, right? Okay? Evaluate that from 0 to 1. These are y's now, okay? This is y equals 0, 1, y equals 0 to y equal 1. Okay, with 1's in there, that would be 5/6 minus 1/6. And the zeros give you absolutely nothing, right? And that gives you 4/6, which is exactly 2/3. That's the one that we're referring to back in example 1 when we were doing the partition of 1/4, and then you did 1/6, and now you get exactly 2/3, 0.66666666667 or whatever, rounded to that. And that's why they said in example 2, you'll see that to be that. Okay. Okay, you want to ask them now? I'm sorry? Okay, well, I've got a student that's going to be coming at 5:30, so I'll need to go. So if it's not going to be more than 5 minutes, it's probably best to go in and ask them now.
Well, it was question 2 and 13.2.
Okay. Okay. I don't have this memorized, so I'm going to have to look. You said on the test, question 2? Is that what you said?
Yes, sir.
Okay. Well, I'm not finding the test. Okay, is that find the limit? Limit is delta x approaches 0 of alpha of x plus delta xy minus alpha of xy over delta x. Is that it?
Yes, we're 8x squared minus 9y.
Right. Okay. Now I can't work that one because that's a test question. So let's go, that would be, what's that? Okay, what page, what section?
891.
8 what, 91? Okay, which one? 11. Okay, it's, I don't think quite the same question, is it?
No, it's not. The limit of delta x. On page 893. Looks like it's 71 or 72.
Okay, yeah, that's it. Right. Okay. Yeah, 71. That looks like a good one. Okay. All right, let's do that one. All right. All right, so we finished example 2. Let me just mark my place here. We finished example 2. We're ready to start example 3, right? Okay. So I'm going to, right here, erase all the ink. You okay too? Okay. And here's what we got. Exercise 71. So this is page 893. This is 13.2 exercises, number 71. Okay. Find the limit as delta x is approaching 0 of f of x plus delta x, y, minus f of xy, over delta x for f of xy is equal to x squared minus 4y. Now that's not the same one that's on your test, right? Right, okay. But it's the same principle. Okay. So what you got to do, the limit as delta x is approaching 0, you got to do exactly what they tell you to. Let's first figure out what f of x plus delta x is. F of x plus delta x y is going to be x plus delta x squared minus 4y, right? Instead of x, you put in x plus delta x, right? Okay, so this will be x squared plus 2x delta x plus delta x squared minus 4y, right? All right, so that's what your first thing's going to be, x squared plus 2x delta x plus delta x squared. My pen is really, 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 really slow. In fact, it's not writing at all. I don't know what the problem is. Let me go back and try to erase some of that. Okay. So let me pick up and go. It just sort of got lost there in the middle. Plus delta x squared minus, and your f of x is x squared, and your, oh, wait. I messed up something. Yuck! My pen's not erasing now. Okay. I forgot the minus 4y. Okay. Minus your f of x, which is minus x squared, minus a minus, which is plus 4y. If it'll show up, divided by delta x. Right? Goodness gracious, this is a pain in the neck. Okay? So that will be the limit as delta x is approaching 0 of, but here you have an x squared minus an x squared, so those add to 0. Here you have a minus 4y and a plus 4y, those go to 0. So what you have here is 2x delta x plus delta x squared divided by delta x. Well, the delta x will cancel that one out in one of those. So that limit will be the limit as delta x approaches 0 of 2x plus delta x, okay? And that would be as delta x is approaching 0, that goes to 0, so this will be 2x. That's an x, not a 4. It's an ugly x. Do you see? Okay, and that's what you do on that one. Okay, was there another? 13.7. Question what? 9?
I think the one similar to it would be 17.
Oh, 17. Okay, I thought you said 9.
Mm-hmm.
Okay, let me see.
I think that sounds better.
All right,
I
well,
started on this one. I
yeah,
did
but it's this one.
something
Yeah. Okay.
Mm-hmm.
All
I
right.
was trying to see where.
Okay, now this is asking for an equation of a normal plane and a tangent plane and a normal line. And the test question is just asking for the normal line, normal vector. Okay. Okay. Well, that's okay. Just a little bit. The normal vector and the normal line are not quite the same thing. Okay, and it was asking for normal vector, right? Okay. Okay. I'm going to try to find the place that you can refer to. Well, let's just do it, and I think it will show up. It's all right to erase this one?
Yes.
Okay. All right. Okay. Let me. I want, yeah. Okay. Keep me from having to look. Just want to make sure of the wording. Number's 9, right?
Yes, sir.
A unit normal vector to the surface. Okay. Now, I want to refer you back to, see, I'm trying to remember which section it is. Okay. So let's just, yeah. Here's what it's referring to. If you've got a tangent plane, okay, the unit vector, normal vector, is perpendicular to the plane. Okay, that's going to have the same directional coefficients, you might say, as that tangent plane. So that's what I was trying to, yeah. And it might be right here. Yeah. The only thing is we got to get it to a unit one, and okay. We're running out of time, so let's do it. And which one did you say? 17?
Yes.
Okay. So this is page 937, 13.7 exercises. Number 17? Okay. Find an equation of the tangent plane, only they're asking for the unit normal vector, right? Of okay. And this will be x plus y plus z is equal to 9. Now that's a plane. And the unit normal vector to that plane at the point, okay. At 333. Okay, first thing I always do is check and see if I plug in 333, 3 equals 3 equals 3, you get 9. So that's on the plane. Okay. Now, it's asking for the, now correct me if I'm wrong, the unit vector, unit normal vector to that plane, or a plane just like this, at that point, right? Okay. I can't think how to best to say it. The normal to that is going to be 1, 1, 1. Okay? That is a vector normal to that. And yeah, that's it.
And then you find that, and that's how you find it.
Right. And let me just, to make sure I'm telling you right, because you see, it's not quite the same as the problem in the book. But let me just make sure. Okay, this is number 9. Okay, just a different problem. Okay. Let me see if I can find, yeah, number 9. Yeah, that's exactly all you have to do. Okay?
I thought you had to find the
Wait. Yeah. Say again?
I thought you had to find the partial derivative for x, y, and z.
Not in this case. In fact, we hadn't done partials yet. in this chapter. Right? This is chapter 13. We did partial. No, we did. Yeah, we did. Yeah, I'm sorry. But that's not required here. Okay. I'm teaching all three classes. I'm getting crossed up. Yeah, you do. Yeah. If this were some shape other than a plane, yeah, then you would do that. But a plane, the normal to it is perpendicular to the plane. I mean, it has to be. So this was really a much easier problem than probably what you were trying to make it out to be. Yeah. Okay. All right. Now, how are we doing on time? Huh? 5 minutes. Do we have time? Where did we leave? Oh, I'm sorry. Was there another question? Okay. Okay. Where we were. Okay, we just did example 2. And we were getting ready to do, okay, we just finished example 2. Did I show you? No, I don't think we showed the answer. Okay. We did it, but let's see how they did it. Because the region is square, it's both vertically and horizontally simple, you can use either order of integration, which is exactly what we determined, right? Okay. And they did, I'm not sure the picture helps any, but this is the square, X and Y are here, the surface is up here somewhere, it's a paraboloid, remember? Because it's square, vertically and horizontally simple, you can use either order. They chose dy dx, I think we did dx dy. Okay, it doesn't really matter. By placing a vertical representation of a rectangle, so they did, the end one is going to be your dx, so do it dx this way. Your first one's going to be dy, so you're going to do a dy's this way. Okay? So they did dy dx to do it this way. Okay? But it really didn't matter. We did dx dy. So we're going to plug it in there then. That produces this. Now, this is a lot like we did, except they're doing their dy first. We did dx first, didn't we? If I'm remembering right.
Yes.
Okay. But see, with this one we do dy. So you do the integral. Just pretend this one isn't even there. Do the integral with respect to y, counting everything else as a constant. So that'll give you a y here, and this will give you a minus 1/2 x squared y, because you treat that as if it's a constant. Minus, and then this will be y cubed over 6, right? Integrating this with respect to y, that would be y cubed, drop that by 1, divide by the 3. You already were dividing by 2, so now you're dividing by 6, right? So they're doing it the other way, which is just as fine. Now, what they did, they grouped these two together because those were just treated as constant times y. We did them separately. It doesn't matter. It really doesn't matter. Okay? Now, we're going to plug in from 1 to 0, 0 to 1, and what you get there is just, now, here, they're skipping steps, which they usually do. This would give us a 1 times y, that 1 times 1, minus 1/2 times 1, 1/2 x squared times 1. So there's the minus 1/2 times 1. And then this gives us a minus 5/1/6, which will give us 1 minus 1/6 is 5/6. And then when you put zeros in, that goes to 0, that goes to 0. So that's exactly what we got before, only we were doing the other first. Now we're doing with respect to x. So it'll be 5, 6x minus x cubed over 6, right? Same thing as we did before, up that by 1, divided by 3. We already were dividing by 2, so it's now dividing by 6. Now evaluate that from 0 to 1. So 1 first will be 5, 6 minus 1, 6, so it'll be 4, 6. Putting a 0 in, but I'll put it 0. And that'll be 4, 6, which is 2/3. Same way we did it, except they did it in reverse order. But the process was just the same. Now, they're skipping example 3, so we're going to pick up on 3, but now I think we're out of time, aren't we? Okay, so we'll pick up and start with example 3 next time. Okay, and let me mark my place here. And then, wow. We got 3 examples of it, 3, 4, and 5. And homework exercises in 14.2, do either 3 or 5. They're both at Calc Chat. 3's at Calc View. Do any of the odds 7 through 11. They're all at Calc Chat. Okay, I think you can do any of the odds 13 to 19. They're all at Calc Chat. 13's at Calc View. And try doing any of the odds 21 to 25. They're all at Calc Chat. 23's at Calc View. Okay. We haven't done one like 27, but I don't think we're going to do one like 27. Let me see. Try doing 27. It should be at Calc Chat. And any of the odds 29 to 33, they should all be at Calc Chat. I think we hold off and we'll do the rest of those later. Okay. All right, any questions? Again, still says my battery is not charged, so still doing